Hello, Further Maths crew. Continuing with our groups today, so just two more sessions, obviously to the holiday, but that takes us very nice to the end of the groups topic. It really is just a top-up of what you've looked at with Mrs James early this year, so it's really just adding a little bit more technical language. To start with, we're continuing with the isomorphisms. You need to be completely aware of everything about groups up to order 7. So within that kind of isomorphisms that you can have and examples of groups within those. So the specification says you have to know up to order 7. However, frequently in exam questions, it asks you about groups of order 8. So it will give you an example of a group and you have to find orders of elements, or you might have to find subgroups. And there are two in particular that are really, really common. So I've also included those two classes of order 8 groups. It won't be a surprise to you to learn that the first one, order 1, the trivial subgroup. So we've just got, just E there. So nothing very exciting is going on. S stands for symmetries, so an irregular triangle, of course, an irregular triangle, all sides. Oh, this looks as if it might be a little bit isosceles-y. So there's a scalene triangle that has no symmetries, so that wouldn't have any more than the one element. This here, cyclic group order 2, Z2, so that's just the integers 0 and 1. Rotations of a rectangle, of course, rotations of a rectangle, you've just got the 180 rotation and then, of course, do nothing, or the 360 notation. You've seen this notation, but it just means E and all the powers of A subject to that condition there. So, of course, theoretically you could keep going, but there's no point because A cubed is just the same as A squared times by A, which is just A. Of course, that's a cyclic group because the powers of A generate all elements of A. Similar with groups of order 3, there is just one set there. These are all isomorphic to each other, so I didn't kind of properly say this one here. So Z2 is isomorphic to rotations of the rectangle, which is isomorphic to this group here. Again, all of these are isomorphic. A equilateral triangle, of course, there are 3 rotations, the 120 rotation and the 240 rotation and the 360 or the 0 rotation. Z3, elements 0, 1 and 2. The elements in there would be E, A and A squared. And of course, all these are equivalent, even though they're very different groups. These are all equivalent. A is a generator, 1 is a generator, 120 is a generator. So they're all cyclic groups. The other thing I've kind of ignored, these are all commutative. So commutative, sometimes known as abelian, so these would all be symmetrical around that leading diagonal. Now, it gets a little bit more interesting when it comes to the groups of order 4. So you'll note that here, I've got it split into 2 different classes. There are 2 sets of groups. Okay, we did this in the starter last week. They're the rotations of the square. So the rotations of the square, so the 0 or 360 rotation, the 90, the 180 and the 270. So that gives us a group of order 4. And of course, you know that is isomorphic to this set of... That I's gone capital, hasn't it? That's a bit annoying. So that's a little I. So it's isomorphic to those 4 complex numbers. I is a generator there, 90 is a generator, 270 is a generator there, also negative i's. And then that similarly is isomorphic to here. So E, A squared, A cubed. The other set, this is a non-cyclic group. So this is isomorphic to the symmetries of the rectangle. So here we were just specifically talking rotations. Here we're talking symmetries. So you've got the 180 rotation and the reflection in the y-axis and the reflection in the x-axis. Of course, there's no way that that can be isomorphic to that, but then you get a different set of elements, different set of groups that are isomorphic to this one. Called the Klein 4 group, named after, I think it was a German mathematician. You don't need to know that, but you might see in textbooks an exam question might use the word Klein 4 group, but then it will also define it for you. This means elements containing powers of E, A and B and combinations as such, subject to these. So you'll see that A squared and B squared is E, and then it's telling you the product AB is equal to the product A. So that means it's a commutative group. But it also means that if we think about the element AB and square that, so if I write that out, AB, I can use that commutative property there, AB with B. And then, of course, what I'm doing here, every time I'm using the associative property, I can change not the position, so I can't switch them around, but I can change just the orders of which I put brackets around. That's C, so it's equal to E. So you can see the order of that is 2, and of course the order of those is 2. Exactly comparable to the order, that being 2, and then 180 rotation. So 2 different sets. Order 5, there's only one group, one class of group. It's a cyclic group, order 5, Z5, so the integers 0 to 4, under addition modulo 5, of course, the rotations of the regular pentagon, and again we've got this power group here. They're all isomorphic to each other. Now 6, we also have a little bit more interesting happening in 6. Again, we looked at these in the last lesson. You've got the rotations of the hexagon, so isomorphic to these two, and then you've got the non-cyclic group. That's the symmetries, so including reflective symmetries as well of the equilateral triangle. That is called the dihedral group. Dihedral group order 6, but you see it referred to as D3 because, dihedral, and of course meaning 2, because even though it's got 3 sides, there are 2 elements for every one of those 3, if you like. So you'll see a dihedral group order 4. They will be the symmetries of the square. This might be a little bit surprising at first. One of these belongs in the non-cyclic group, one of these becomes in the cyclic group. And the only difference is really this thing with the AB, BA. There you've got AB equaling BA squared, but that definition, of course, means it's a commutative one. Doesn't matter the order in which you do the rotations, it's the same whichever you do first. But here, for some instances, doing a rotation and a reflection, you'll get a different result than if you do that rotation and then the reflection. Did I say that right around? Don't know, but check back at our group tables from last time. So there, that you can see is not commutative. If it's commutative, AB will be equal to BA as in there. 7, there's only one. 8, so I put a little note down here. There are 5 classes in total, so there's a further 3. But I put these 2 on because these are the most common and they're directly comparable to these 2 and these 2 here. In that you've got one group of 8 that's the cyclic group, that's of course just the rotation. So you see every time there's a number of sides going up, we've got a rotational group. Just powers of A. You have a slightly different property there, but you have the commutative property there. So it's commutative. The second class, all right, so this is what I was talking about up there. Dihedral group order 4, so that would be denoted D4. They won't expect you to know that. They might refer to it in a question, but they'll give you the information to back it up. The symmetries of the square, so that means reflective and rotational. When it's just rotations, I'll put that there. And again here, you can see that's a non-commutative group. Now, whenever you are asked about any groups, or whenever I'm asked about any groups, every single time I'm thinking about the symmetry group that's equivalent to. This particularly, can be quite hard to get a hold on. Sometimes you're given groups that have just got the tables, they've just got the information, so there's no clue as to what it is. But because I understand really well what the symmetries are, it makes it easy for me to pick subgroups, to think about properties of elements and so on. One final kind of thing, all of the prime groups I've kind of just left in white. All groups of prime order have got no proper subgroups. If you think about this one here, order 4, your rotations, you know that there's a 0 and a 180. They're going to form a subgroup. Here, again, there's the 0 and the 180, but then there's all the reflections. There's your identity, and then there's the reflection in the x-axis. They form subgroups as well. You're not going to have any subgroups here because you can't just get those fifth of a turns and taking 1/5, 2/5 and 3/5. That's not going to work. You need to either take them all or none at all. So everything with prime order doesn't have any proper subgroups. We are focusing more on subgroups today. Subgroups you looked at with Mrs. James. So that's the reminder of the definition. Oh, here we've got a subgroup. This is just a brief example of what you've already looked at. 1, 2, 3, 4, 5, 0, 2, 3, 4, 5, 0, 1. So what we're looking at here is the integers addition modulo 6, and I've got one more line to fill in. So when asked for subgroups here, I would think symmetry. And I know that Z6, that's equivalent to a 60-degree rotation. That would be 120, that's 180, 240 and 300. So when I'm asked about subgroups, I know that I would have the 0 degree and, I'd have the 180. So that's equivalent to 3. And I know you can get from the table because 3 plus 3 is 0, but I'm just trying to emphasise the fact that using the symmetry groups is the easiest way to think about these. And then I know, you can kind of like faff around with the numbers, and I'm sure you know, well, if I just take 0, 2 and 4 and add 2 and 4, I get 6, and that's fine, that's closed. But I know that 120 plus 240 makes 360. So, of course, and there's no point in looking for any others. You might think, 0, 2 and 4, so maybe 1, 3 and 5, but of course not, because you're not going to have the closure then, because 1 plus 1 makes 2. So that takes you outside of the group. They're the only proper subgroups, so you'll remember that as well from last year. It's a bit like they're classed as proper factors. Here you've got the two, dull, non-exciting, trivial subgroups. So they're the proper ones, and these ones are the trivial ones. So to prove that something is a subgroup, you've got to show, first of all, that it's a subset. Now, this can catch people out because as part of the fact that it's a subset, that you'd need to check that this particular subset satisfies the group rules as well. Okay, so it might be that you've got some matrix group and everything looks fine and you multiply two matrices, that's fine, but then there was also a little clause that said, okay, the determinant's got to be 1. So, next door are having a new bathroom and everything had got a bit silent, but sorry, the drilling started. I'll keep going for a bit and see what happens. So you've got to show that the set is closed, you've got to check that the identity is also there, and then check that every element has got its inverse. So here we've got a group. This Z0 plus, well, just Z plus is fairly common. That just means the positive integers and n just means we're including 0. Written like that because sometimes the natural numbers, there can be a bit of confusion. Really, that's just the counting numbers from 1 upwards. So that's just to emphasise the fact that we are including 0. That stopped, hopefully, for a long time. Explain why that's not a subgroup of Z, meaning the integers under addition. So, first of all, is it a subset? Well, yeah, it's clearly a subset. Yep, so we've got a subset, that's fine. Then if we check and see if it's closed, well, yeah, of course it is, because if we take 2 positive integers and add those, we're going to get another positive integer. The identity, yes, the identity is there because 0 is in our particular set. Inverse, however, inverse, no. I know that the inverse of the element A is negative A, and negative A is not in H. We haven't got any negative numbers in there as well. What I've done there, explain why. Of course, you needn't have gone through that, and that. You could have gone straight for the thing. And explaining why, so this is a little bit wordy. If I'd been asked to prove it, I'd have been a bit more particular. I'd have said something like, let A be an element which is in Z0, and the inverse of A is equal to negative A, but negative A is not contained in Z0. Sorry, in Z0, hence H is not a subgroup. So a little bit of difference, isn't it? That's my kind of chatty, explainy. That's a bit more of a proof. So, think about whether the technical language is needed or not. Here, this set, so again, we're talking about an infinite group, and then we're taking out all things that can be written as 12x plus 21y, proves that that's a subgroup of Z. So, show that it's a subset. So we have to carefully spell out, and it might be obvious, it will be obvious, well, of course it's an integer, but it's a proof. Look, it says proof. Some of you need to be a little bit more careful about spelling things out, even when it's obvious. So if x and y are integers, then this expression here is also an integer, so h is a subset. Okay, that's fine, that's great, but you need to write it down. You can use some symbols, of course. So rather than saying are integers, you can use that symbol there, but you've got to spell it out. Now, the second thing we had to do was to show that it was closed. To show that it's closed under addition, so we want a different, we want 2 different things, so I've called them P and Q. Then write P in terms of the individual components and Q in terms of the original components. Add those together, yep. So it can be written as 12 multiplied by some integers plus 21 times by some integer. And again, many of you will just write down, it's obvious, but you've got to try and write down a justified proof. Both x plus u and y plus v are also integers, so hence it's closed. So I would maybe just h is closed under addition, just add that comment. Right, the identity. The identity, so this is nice, isn't it? The identity, say what the identity is, then, okay, that's in H. So, yeah, that's fine. So identity is in H. But you have to, so you couldn't just say, oh, the identity is there, it's fine. Or some of you, I can imagine putting identity and then a little tick. Say what it is, say why it's there. And then inverse, so this is where the other one kind of fell down. So if we consider a particular element, then I've written down what my element is. And look, I'm saying what the inverse of the element is. The inverse is that, and that is in H. Hence, it's a subgroup. All of those 4 things have been satisfied. Now, I'm sure this is something that Mrs. James mentioned, Lagrange's theorem. So Lagrange's theorem says tells us about the order of subgroups. Now, whenever you've been writing down any bunch of subgroups, of course, just the way the elements fits together, it's kind of fairly obvious. But the order of any subgroup must be a factor of the order of the group. So if you've got a group with 6 elements, your subgroups are going to be 2 and 3, well, your proper subgroups. If you've got a group of order 8, your subgroups are going to be of orders 2 and 4, of course 1 and 8 as well. So it's exactly kind of like factors, you know, of just numbers of integers. The proof itself, don't need it. It's kind of similar to the proof of finding inverses of 3 by 3 matrices. It talks about cosets, left cosets, right cosets. I've included a proof, but it's taken from an undergraduate course. You just don't need to know it as well at all. This, you need to, you just kind of need to know that as well. That's something I referred to on that first sheet. Now, this example here. You're given that this set, the integers from 1 to 12 forms a group under multiplication modulo 12. Find a subgroup of these orders or explain why none exists. Now, whenever Lagrange's theorem is needed, it's always given 2 marks. It's given 2 marks because you have to talk about factors. You need to state what the theorem is and mention him by name. And I've kind of bigged this up because, again, I can imagine some of you, well, it's just obvious, isn't it? And just writing down the factors. You are using a particular theorem, you need to state what this is. So, 2 marks. It's going to be given 2 marks. So for this first one here, I say, right, my group is of order 12 and 2 is a factor of 12. I know that's obvious. That will be obvious from, you know, when you're 6. But you need to write it down. So by Lagrange's theorem, we've got a subgroup of order 2. So 2 very distinct statements, talking about the group, talking about the particular subgroup order, and then applying Lagrange's theorem. Now, finding the subgroup, you could draw the table out, but it's going to be a 12 by 12 table. It's going to be a right faff. There are going to be some big numbers there. I can't be bothered to. So what we're going to do is try and think about how we can do this without drawing the subgroup. I need to think about what the elements are going to be, and because I know my, my grouped table here, so because I know intimately well all of my groups up to 7 orders, I know, right, okay, so I've got obviously the identity, and then my second element is a self-inverse, so I want something squared that gives me the identity. So what you are looking for is something that contains the identity and a self-inverse. So the identity is, of course, 1. It's a multiplicative group. And then I want something that's, so if you kind of think about just squaring the numbers, square 25, no, that doesn't work. If you square 12, you get 144, and 11 times 13 is equal to 143. So, of course, that's congruent to 1, so 12 is the self-inverse. So I know my subgroup of order 2 is 1 and 12. Right, now we go on to 3. When we go on to 3, we again state our Lagrange's theorem. The group is of order 12 and 3 is a factor of 12. Okay, so by Lagrange's theorem, there is a subgroup of order 3. So we need to find it. So if I look here again, subgroup of order 3, we only have cyclic ones. If you think about the elements there, the other 2 elements other than a cubed, a and a squared, multiply together to form e. Think about it in terms of rotations. I've got my 120, my 240, they combine to give 360. So what we are looking for is a paired inverse. So somewhere down here, group of order 2 must contain the identity and a set of paired inverses. So multiplying 3 by 9, oh, that's 27. 27 is 1 above 26. So 3 and 7 are paired inverses. So you might think, well, hey, there we go. So I've got 1 3 and 9. Not 9, it's 7, 1, 3. Hang on. Yes. So that, apologies, should be a 9. So 1, 3 and 9 is my group. But what you must do first is check that you've got closure. So it's all very well saying that these are paired inverses, but 3 squared, yeah, 3 squared does equal to 9, so that's fine. 9 squared, 9 squared is equal to 81. And 81 is congruent to 3 mod 13, so that's closed, that's fine. And it doesn't always happen. So what I've just shown down here is 5 times 8, 5 8s are 40. That's also congruent to 1 mod 13. So you might think, oh, there's another group, and in that group is 1, 5 and 8. However, 5 5s are 25, which is congruent to 12 mod 13. So that wouldn't be closed. So you might think, well, it's a bit dangerous because I didn't draw the group table. However, as long as you just check you've got that closure, it's fine to do it just by looking at your knowledge of groups and your knowledge of elements. Here, of course, there's going to be none. You know there's going to be none. You know that by sight, but it's going to be worth 2 marks in the exam, even if it's worth 1 mark. Okay, you need to make sure you get everything. The group is order 12, but 5 isn't a factor of 12, so Lagrange's theorem says there are no subgroups of order 5. You have to write down both bits. Okay, so moving on. So what I've done here is I've got an awful lot of words. All of these words are trying to kind of help you go through my thought process, because sometimes when we've got really big groups, it can be hard to spot what the subgroups are. So here I've got a group. This group, it's got 8 elements in. I kind of know a little bit about things with 8 elements. And what I've said here, before I'm even going to start focusing on subgroups, I'm going to just look at the structure. And in particular, if I look along this leading diagonal, I've got E, Q, E, Q, R, and then I've got all of these E's. What that means, of course, is I've got an awful lot of self-inverses. So I'm already thinking I know what that group is. And again, I've lost my tables. Here it is. This group, I'm thinking very much it's going to be this dihedral group here, because we've got all these self-inverses, all the self-inverses where firstly I have 180-degree rotation, and then I've got a reflection there, a reflection there, a reflection there, and a reflection there. So 5, of course, the identity itself, but other than that, I've got 1, 2, 3, 4, 5 self-inverses, so I'm thinking that's what it is. And you might even, in an exam question, think, okay, so I reckon that might be the 180, this might be the 90, that might be the 270, and then all of these are the reflections. Okay, so find all the subgroups. What you would do if this was an exam, you would apply Lagrange's theorem. Since the group is order 8, by Lagrange the possible orders are going to be 1, 2, 4 and 8. Most exciting ones, of course, are 2 and 4. Order 1, trivial subgroup. Order 2, so I know that if anything's got order 2, it's got a self-inverse, and of course we can easily identify these by looking down that leading diagonal. So I'm going to have E and Q, I'm going to have ES, ET, EU and EV. So that's just what I have said there, and there are those 5. Don't need to do all the 3, it's not a factor. Now I'm looking at order 4. Now, if this is a D4 group, of course I know that I'm going to have 1 from the 0, 90, 180 and 270. That, of course, is the cyclic group, order 4. It's commutative. It's fairly easy to spot, and I think you've seen enough of these to know pretty much every time you've got this cyclic group, every time you've got the non-cyclic group, we've got this nice little subgroup appearing here, and that refers to the cyclic group of order 4. So that is our cyclic subgroup happening within our non-cyclic group of order 8. So I have got E, P, Q and R. So that is the first one. I'm not going to have any more cyclic ones because every other element has got a reflection involved. But I know that if I have 180 together with that and that is going to get me one subgroup. I also know that I potentially might have that and that together with the 180, but in either case, I have to have this self-inverse because you're going to have, so I'm looking here. So I know I'm going to have the 181, that is a self-inverse. So I've got one element taken up by the identity itself, one element taken up by the 180. So that's a self-inverse, that is the inverse. And then these other ones are going to be a paired inverse. So because I definitely know I've got E and this, and that I already know is the Q, I can make things easier by, I'm going to just highlight down here, highlight that. So I know whatever else is in there, these two have got to be in here. And then I am looking for two elements from here. And if I look at the lines that I've highlighted, S and T, T and S, okay, so what do you reckon to E, Q, S and T? So S and T, if I check out S with S, that's E. If I check out T with T, well, of course, that's E. What if I check out S with T is Q? Yep. And T with S is Q. Yep. So that's great. That's good. That's one definite group. And again, if I look here, I've got UV, oh, VU. Just check for closure, V with V, and of course U with U works, but what about U with V? U with V is Q, and V with U is Q. So that's the other group. So essentially what I've tried to do there is summarise all the stuff that I've just spoken about. So I've talked about, deleting, highlighting things. So they're my subgroups. And order 8, that is a subgroup as well, and just summarised all of those. So just another couple of little results following on from all of that. I think this is what I've said. The order of an element of a finite group is always a factor of the order of the group. So all those individual elements, because I've got a group of order 8, the individual elements can only have orders 1, 2, 4 and 8. So you're never going to have an element that's got an order of 5 within a group order 8. So that, again, just kind of falls from the combinations of all elements, and I know you'll have spoken about that with Mrs. James as well. Don't need to know the proof for that. If a group has got prime order, it's always cyclic. So think back to the table. All of those were cyclic. They never had any proper subgroups because if they're cyclic, one element just generates everything. Each element has order P again. Because of that prime order, they're all kind of essentially intertwined. Okay, so that is it, essentially. The questions that I have, these first 3, kind of just very nice, find all the subgroups, try and think symmetry groups if you can. Bear in mind, however, that there are 5 classes of groups order 8. We've spoken about 2 of them in particular. Here are 3 groups, so probably one of those groups isn't the 2 symmetry groups that are on this table as well. However, any subgroups are of order 2 or 4, and you know how they work within there in particular, so kind of think about combinations. And then there's just 2 questions taken from the book as well. Okay, hope that all goes fine. Groups, I think we like groups, don't we? So I'm not envisaging any problems. Last lesson tomorrow, we're going to get more kind of stuck into a little bit of awkward algebra, but not too tricky. Okay, see you tomorrow.